Good morning, students. This is next topic in D block of block elements, that is magnetic properties. That means these elements exhibit magnetic properties, whether it is diamagnetic or paramagnetic. Now we are going to discuss about that one. See, the substances which are attracted by magnetic field is called paramagnetic substances. That means when any substance attracts towards magnetic field, those are called paramagnetic. The substances which are repelled by magnetic field is called diamagnetic substances. If the substances which are strongly attracted by magnetic field, those are called ferromagnetic. Simple points. There are only 3 points are there. If they are attracted by magnetic field, those are para. If they are repelled, they are considered as diamagnetic. If they are attracted strongly by magnetic field, those are called ferromagnetic substances. So here what we have to know one point. What is the condition to exhibit paramagnetic? What is the condition to exhibit diamagnetic? See, the ions which are having unpaired electrons, which exhibit paramagnetism. That means if an ion having any unpaired electrons, then those ions exhibit paramagnetism. That means those ions easily attracted towards magnetic field. If suppose they are absent, they means unpaired electrons. If those are absent, then they don't attract towards magnetic field. That is nothing but diamagnetism. So only 2 points are there. The ions which are having unpaired electrons exhibit paramagnetism. The ions which are not having unpaired electrons are completely filled d orbitals exhibit diamagnetism. Here the magnetic moment, not movement, the magnetic moment, that is represented by mu, it is calculated by this formula. That formula is root of n into n plus 2 bm. Bm means Bohr magnetons. This is dimensions. These are the dimensions of magnetic moment. So this is the formula to calculate magnetic moment of given substance, nothing but given ion, where n is number of unpaired electrons, in d orbital. If number of unpaired electrons increases, that means mu also increases and paramagnetism also increases. This is also important point, where n is number of unpaired electrons. If number of unpaired electrons increases, magnetic moment increases and paramagnetism also increases. So these are the examples. For example, take Cr plus 2. This is ion. For this, the electronic configuration argon 4s0 3d6. This is outer electronic configuration. In 3d6, actually 6 electrons are present, but we have to consider only unpaired electrons. We should not consider total electrons present in d subshell. We should consider only unpaired electron. So d subshell contains 5 d orbitals. Among 5 d orbitals, 1 orbital having 2 electrons. That means that is paired electrons. The rest of 4 orbitals having 1 electron. That is called unpaired electron. So how many unpaired electrons present in 3d6? 4 unpaired electrons. So that its magnetic moment is what? 4 into 4 plus 2. Finally 4 into 6. That means root 24. Root 24 value almost 4.9. This is approximate value, not accurate value. One more example, Cu plus 2. Its outer electronic configuration is what? 4s0 3d9. This is 3d9 configuration having only 1 unpaired electron. What is the formula? Mu equal to root of n into n plus 2. So root of 1 into 1 plus 2, finally root 3 almost 1.732. In this case, one more example, 4s0 3d5. 3d5 having 5 unpaired electrons. So 5 into 5 plus 2, 35, almost 5.9. So this is the way to calculate number of unpaired electrons. So what we have to know here, you just know about electronic configuration. You have to know electronic configuration to calculate magnetic moment. Next, that is all about magnetic properties. Next topic is color of the transitional metal ions. Color of the transitional metal ions. See, transitional metal ions exhibit color in aqueous solution due to DD transition. Transitional metal ions exhibit color in aqueous solutions due to DD transition. DD transition means if an electron jumps from one d subshell to another d subshell, or one d orbital to another d orbital, then they exhibit color. That is the meaning of that point. In the presence of ligands, I will discuss later about the ligands. Until then, you just remember, in the presence of ligands, the d orbitals will split into two groups of orbitals. This is called crystal field splitting. This is a very important point. Still, we don't know what is ligand. I will discuss about it later. In the presence of ligands, the d orbitals will split into two groups of orbitals. This is called crystal field splitting. The metal ions having unpaired electrons, absorb one color from visible region. Then it jumps from lower orbitals to higher orbitals. There, the energy of the electrons is very high, so that it undergoes de-excitation. De-excitation means electron jumps from higher orbit to lower orbit. Due to that, it exhibits complementary color, that means opposite color. That color is the responsible for the color of the transitional metal ion. This is the reason behind exhibiting color by transitional metal ion. I will explain once again. Listen carefully. When a metal having unpaired electron, when we pass light to that metal ion, then the electron gain energy from the light, so that the electron jumps from one d orbital to another d orbital. There the energy of the electron is more, but stability is less. To get stability, it undergoes de-excitation. That means it again jumps from higher orbit to lower orbit. In that process, it emits one color. Why it undergoes excitation initially? Because it absorbs light, nothing but it absorbs energy, nothing but it absorbs color. That means it absorbs one color, but while de-excitation process, it exhibits one color. That is complementary color, nothing but opposite color. That opposite color is the responsible for the color of the transitional metal ion. See, for red color, green is the complementary color, or vice versa. For orange color, violet is the complementary color. For blue color, yellow is the complementary color. That means if a substance absorbs red color, then it emits green, or if a substance absorbs green, then it emits red. That is the meaning of that point. Similarly, in case of these two cases also, same phenomenon takes place. Next, if transitional metal ions containing unpaired electrons, then they exhibit color. We discussed it. If unpaired electron is present, then only they exhibit color. How can we know whether the ion present having unpaired electron? By using electronic configuration. So that here you have to learn clearly about the electronic configurations. That means how to write electronic configuration. That is very simple. We have discussed already those points in class 11 in first chapter. So without writing electronic configuration, we cannot find a paramagnetism, nothing but paramagnetism, diamagnetism, and we cannot find whether it is exhibit color or not. Next, if the transitional metal ions do not contain unpaired electron, then they don't exhibit color. If they are having unpaired electron, they exhibit color. If they don't have unpaired electron, then they don't exhibit color. That's all. This is very simple topic. Based on this, some questions are there. We will discuss those questions now. First question: why anhydrous CuSO4 is colorless but hydrated CuSO4 exhibits color? See, anhydrous CuSO4 means copper sulfate having no water. That is the meaning of anhydrous CuSO4. Hydrated CuSO4 means copper sulfate having water. I will repeat once again. Anhydrous CuSO4 means copper sulfate having no water. Hydrated CuSO4 means copper sulfate having color. So, what is the copper sulfate having water? So, what is the meaning of the question? Why copper sulfate, anhydrous copper sulfate is colorless and hydrated copper sulfate is color? That is the meaning of the question. The answer for that question is in anhydrous CuSO4, crystal field splitting does not take place due to absence of ligands. That means in anhydrous CuSO4 there is no ligand, so that there is no chance of crystal field splitting, even though presence of unpaired electron in Cu plus 2. But in hydrated CuSO4, crystal field splitting takes place. That is due to the presence of ligands. Due to the presence of ligands, then crystal field splitting takes place in Cu plus 2 and in case of hydrated copper sulfate, so that it exhibits color. So that is the answer for that question. That is one of the important question. Next, one of the very important point regarding this topic, that is the compounds came in for nothing but potassium permanganate, potassium dichromate and potassium chromate exhibit color due to charge transfer phenomenon. Here one important point is that in all these cases, in KMnO4, manganese is the central atom and it exhibits +7 oxygen state. Actually, Mn electronic configuration is what? Mn 4s2 3d7. Sorry, 4s2 3d5. But in Mn +7 oxygen state, there is no unpaired electron. Even though absence of unpaired electron, this KMnO4 exhibit color. Next, K2Cr2O7. In this case also chromium exhibit +6 oxygen state. You can find it. In that case also chromium having no unpaired electron, but it exhibits color. In case of K2Cr4 also chromium exhibit +6 oxygen state. In all these cases, central atom having no unpaired electron, even though absence of unpaired electron, they exhibit color. That is due to charge transfer phenomenon. So because of charge transfer phenomenon, these three compounds exhibit color even though absence of unpaired electron. So that is all about color of the transitional metal ions. Next topic is alloys. Alloys are the homogeneous mixture of metal with metal or metal with non-metal. The homogeneous mixture of metal with metal plus metal or metal with non-metal is called alloys. These are prepared to modify the properties like malleability, ductility and resistance to corrosion. That means to make sheets, to make wires and to do not undergo corrosion. For all these purposes, we used to make alloys. Some alloys are there given. They are bronze, brass, German silver. In bronze, 2 metal atoms are present. They are copper and tin. Copper percentage is like this 75 to 90 and tin percentage is like this 10 to 25%. In case of brass, copper percentage 60 to 80 and zinc percentage 20 to 80. In case of German silver, copper percentage 50 to 60, nickel percentage 10 to 30 and zinc percentage 20 to 30. That means here 3 metals are present. So alloys nothing but mixed metals. Here in one important point is that regarding German silver, in German silver, name itself silver is present, but in German silver the composition of silver is 0. The composition of silver is 0 because in the German silver only copper, nickel, zinc, only these elements are present. So this is about alloys. Next, interstitial compounds. This is also one of the important topic and very small topic. This is also called non-stoichiometric compounds. That means those compounds which are not having specific composition. That is called interstitial compounds. The compounds which are formed by trapping of carbon, hydrogen and nitrogen in crystal lattice. That means in crystal lattice small gaps are there. In that small gaps, suppose if these elements are trapped, then these compounds will form. Such compounds are called interstitial compounds. For example, Mn4n, ZrH1.5. These are example for interstitial compounds. These are also called non-stoichiometric compounds. That means in these compounds, composition is not perfect because these elements are trapped in the gaps of the crystal. Next, properties of the interstitial compounds. They are chemically inert. Inert means they do not react with any other substance. Next, they have more melting point because these elements are trapped. Automatically, melting point will be more. Next, they retain their conductivity. They retain means Before trapping elements, they have conductivity. After trapping elements also, they have conductivity. That is the meaning. Next, they are very hard. So these are the properties of interstitial compounds. This is about interstitial compounds. Next, last topic in this chapter, in D block elements, that is catalytic properties. That means what? Most of the elements exhibit as catalyst in chemical reactions. For example, N2 plus 3H, this is Haber's process. In this process, iron is the catalyst. Iron is what? D block element. In second reaction, that is what? Contact process. In this process, platinum is the catalyst, and vanadium pentoxide. Vanadium is a transitional metal oxide, that is also catalyst. Next, in this case, potassium chloride. In this case, also MnO2, manganese dioxide, is the acts as catalyst. Next, when olefins reacts with hydrogen, that means olefins undergoes reduction, then alkenes will form. That means olefins means what? Alkenes. When alkenes reacts with hydrogen, then double bonds will become broken, then single bonds will be formed. Those are called alkenes. That reaction takes place in the presence of nickel. That nickel is what? Transitional element. So these are the examples regarding catalytic properties. So this is all about D block elements. Now we will discuss about F block elements. That is also very small topic. See, F block elements. What is the definition? The elements in which the differentiating electrons enters into F subshell are known as F block elements. These are present at the bottom of the periodic table. We know that. Next, it contains two series. They are 4F and 5F series. 4F series elements are called lanthanides, and 5F series elements are called what? Actinides. Here, the atomic number from 58 to 71 are called lanthanides. These elements are also called rare earth metals because they occur rarely in the earth. That is why they are called rare earth metals. They are cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. So now most of the topics also removed from F block elements from CBSE level in this year. So no need to remember about these elements, these symbols, these atomic numbers and electronic configuration in this case. Here are two questions are there. I will discuss those points, and one important question is also there. Those are enough regarding F block elements. Next, the general electronic configuration of lanthanides that is 6s2, 4f1 to 14 and 5d02 because this is 4f series. Next, in these elements, promethium and samarium are radioactive elements. Next, oxidation states. The common oxidation state of F block elements is +3. In case of D block elements, +2. Next, lanthanides also exhibits +2, +4 oxidation state. Next, cerium 4, that means cerium in +4 oxidation state is used as analytical reagent. Analytical reagent means that compound can be used to estimate the other compound in volumetric analysis. Next, the ions having 4Fn and 4F14-N exhibit same color. The ions having 4Fn configuration and 4F14-N configuration exhibit same color. For example, Pm+3 and HO+3. Both are having same electronic configuration. By using this, you can write the electronic configuration. Then you get same configuration in both cases. Same configuration means if 4F6 is here, so in this case 4F14-6 becomes 4F18. That means 4F6 and 4F8 having same color. That is the meaning. So Pm+3 and HO+3, Eu+3 and Tb+3, Dy+3 and Sm+3, these exhibit same color because they are having same electronic configuration. Next, in +2 state, they act as reducing agent, and in +4 state, they act as oxidizing agent. These elements exhibit +2 and +4 station also. So the elements in lower oxygen state act as reducing agent. In higher oxygen state, they act as oxidizing agent. Next, in +3 state, they act as both reducing and oxidizing state. That means in intermediate state, this is +3 is the intermediate oxidation state. In that state, they act as both reducing agent as well as oxidizing agent. This is the next topic, that is lanthanide contraction. Contraction means less. That means what? Size becomes less in case of what? Lanthanides. That is why it is called lanthanide contraction. So the definition for that is the atomic size gradually decreases in lanthanides due to poor shielding effect or poor screening effect of 4f orbitals. That means in lanthanides, I told you already, that is comes under 4f series. That means in all lanthanides 4f orbitals are present, but these 4f orbitals having less screening effect. That means what? The electrons which are present in 4f orbitals cannot act as screens to outermost electrons. Automatically the nuclear attraction will be more on valence electrons, nothing but outermost electrons. Thereby attraction will decrease. That happens in case of lanthanides. That is why size will decrease. So that is called lanthanide contraction. Next, consequences. That means effects. Because of less size, the separation of lanthanides is very difficult from their mixture. That means if all lanthanides are present at one place, we cannot separate those lanthanides because all are having almost the same size. That is the point. Next, the atomic radii of 5d series elements and 4d elements are similar. I told this point already in first part of the video. So what is the point? 4d and 5d series elements having same atomic radii because of lanthanide contraction. Next, these are the examples: zirconium, osmium, niobium, tantalum, molybdenum, tungsten. Next, from lanthanum hydroxide to lutetium hydroxide, basic nature decreases. Due to covalent nature increases. That means from here to here, what they are telling, these are hydroxides. These hydroxides having basic nature, their basic nature decreases due to covalent nature increases. Because of that reason, basic nature decreases. Why? Suppose if covalent nature increases, then bond strength increase. If bond strength increase, bond energy also increase. That means there is no chance to break the bond. If there is no chance to break the bond, then hydroxide ions will not release. If those hydroxide ions will not release by those atoms, those molecules, then basic nature decreases. That's all. I repeat once again that point. Covalent nature increases means bond strength increases between, suppose for example, take this one. In this case, LuOH thrice. Between lutetium and hydroxide, covalent bond strength is more. If covalent bond strength is more, then bond energy will be more. If bond energy will be more, then that bond cannot be broken easily. Then OH minus ions cannot be released by LuOH thrice easily. If those are not released easily, automatically basic nature decreases. So this is also one of the definitions regarding basic nature. Next, chemical properties. That means when lanthanides reacts with acids, then they liberate H2. That means hydrogen gas. When any lanthanide reacts with any acid, then hydrogen gas will be liberated. Next, L means all lanthanides. When lanthanides reacts with sulfur, then lanthanum sulfides are formed. When lanthanides reacts with water, then lanthanum hydroxides will form. When lanthanum reacts with halogen, then lanthanum halides will be formed. When lanthanum reacts with nitrogen, then lanthanum nitrides will be formed. When lanthanum reacts with oxygen, then lanthanum oxides will be formed. Next, when lanthanum reacts with carbon, then lanthanum carbides will be formed. These are the chemical properties of lanthanides. No need to remember because this is not there in our syllabus in this year. Next, actinoids. The atomic number from 90 to 103 is called actinides. Next, the general electronic configuration of actinides is 7s2 5f124. These general electronic configurations are important. In case of lanthanides, 6s2 5d021 4f1214. But in case of actinides, 7s2 6d01 5f1214. Then what is the general electronic configuration of a block elements? ns2 n-1d021 n-2f1214. Next, these are also called transuranic elements. That means radioactive elements. Next, here these two questions are also very important. Next, why? What is the question? Why actinide contraction is more than lanthanide contraction? That means compared to lanthanide contraction, actinide contraction is more. Why? That is the meaning of the question. Here the point is lanthanide contraction causes due to less screening effect of 4f orbitals. That means those 4f orbitals present in fourth shell. Actinide contraction is causes due to less screening effect of 5f orbitals. So what is the reason here? The screening effect of 5f orbitals is less than 4f orbitals because 4f orbitals are somehow close to nucleus. But these 5f orbitals are present in fifth orbit. These are present in fourth orbit. Compared to fourth orbit, fifth orbit is somehow far from nucleus. Automatically, these are having less screening effect. In this case, more nuclear attraction will be present on valence electrons. Automatically, size will be less. So that is the reason behind this one. So what is the point? The screening effect of 5f orbitals is less than 4f orbitals. Hence, actinide contraction is more than lanthanide contraction. That's all. This is very, very important question for 1 mark. Next, one more question. Why actinides exhibit more number of oxidation states? OS means oxidation states than lanthanides. That means lanthanides exhibits only +2, +3, +4, but actinides exhibits +3, +4, +5, +6, +7, so many. Why? What is the reason behind that one? So what the reason for that is, in actinides, the energy difference between 7s and 5f orbitals. 7s, that means this is 7s and 5 orbitals, energy difference is very less. If energy difference is very less, automatically those electrons will be involved in bonding when they react with any other substance. Automatically more number of oxidants will be formed by actinides. So what is the reason? In actinides, the energy difference between 7s and 5 orbitals is very less. Hence they exhibit more number of oxidation states. So this is also one of the important questions. So in F block elements, you should learn electronic configuration of lanthanides, actinides, and electronic configuration of F block elements. Next, lanthanide contraction consequences and these two questions. You just learn these topics only from F block elements. No need to learn rest of the topics in F block elements. This is all about D block and F block elements. In next video, we will discuss about complex compounds chapter. Thank you.